did it not print? Let's see, where is it? I missed a page. It's the calculus. Oh, the calculus of energy diagrams. This was the best one. It's the calculus of energy diagrams. I can do it in like 2 minutes, and we have 5 left, so, you know. Okay, it just is totally messing up my flow here, you know. We were supposed to end on chemical bonds to like roaring applause, and everybody goes out high-fiving. And now we're ending on calculus. Oh, well. You lose some when you teach intro physics. Is the bond, yeah, so the bond length, so my drawing went to crap here. The bond length is this physical distance in x. It's like I'm saying that the ball ends up at the bottom of this well, and how far is it from the origin? Right, I put this at the origin, and this was moving around in x. So it's just how far apart they are. Okay, so then the exciting part, is the calculus of energy diagrams. Okay, so we know that the change in potential, we've been plotting the potential, is the external work that you do. Sort of talked about that earlier. You do work on something, you lift it up in the air, and you put it on a shelf. You did work to increase its gravitational potential. We know the work is the integral of the force you applied over some distance, right? So this looks like the fundamental theorem of calculus. The integral of this equals u final minus u initial. Remember the fundamental theorem of calculus? If this was the change in position, it's the integral of the velocity times time. Well, now we have the change in of energy of the integral of the force times position. That means we can rewrite it the other way. We can apply the fundamental theorem of calculus and get that the force is the negative du dx. All right? I forgot to think about and explain where the negative comes from. It's because whether it's external work or internal, don't worry about it. Just accept for now. We will talk about the negative sign in office hours. That the force is negative du dx. So let's look real quick what that means. All that means, and to use it mathematically, is anywhere you go on this slope or on this curve, if you want to know the force that the ball is actually feeling, you just take the derivative of whatever is making the potential. So here would be the force is the negative derivative of 1/2 kx squared. Okay, negative 1/2 kx squared, the derivative is kx. It's Hooke's law. Right? So any potential I give you, say if I give you the potential is 3 plus 12 squared plus x squared plus x to the 10th. And you'd say, I need a function for the force. What is it? Minus 2x minus 10x to the 9. Just take the derivative and make it negative. Okay? And then you have the force anywhere you go. Okay? But that's just that's just sort of the definition of the relationship between force, work, and energy, is that it looks like calculus. It is calculus. Okay? Okay, so that was not in the right place. Whatever.